हेलो विद्यार्थी मित्रों, चैप्टर नंबर 1, lecture number 6. Last time we were discussing exercise 1.2 of NCERT. Only few examples we need to see from exercise 1.2, only 3 examples, rest of are solved. Example number 8. So that from A cross B to B cross A, such that f of AB is equal to BA. Bijective function where A and B are two sets. Clear? Now see here. We know that what mean by bijective function. A function is 1, 1 and 2 is called bijective function. Here A from A cross B to B cross A. F of AB is equal to BA. Clear? To show it is 1, 1, let us consider for A1, B1, A2, B2 belongs to in domain of function. Consider f of A1, B1 is equal to f of A2, B2. This implies B1, A1 as per definition is equal to B2, A2. When we say that two order pairs are same, corresponding elements are same. Clear? And this implies A1, B1 is equal to A2, B2. So what we seen? And therefore, for A1, B1, A2, B2 belongs to A cross B, f of A1, B1 is equal to f of A2, B2 implies A1, B1 is equal to A2, B2. And therefore, f from A cross B to B cross A is 1, 1. Now, what is range of f? Is equal to order pair f of AB, where order pair AB belongs to A cross B, is nothing but order pair BA. B belongs to B and A belongs to A, is nothing but B cross A. So what we seen? And therefore range of f is equal to B cross A. And therefore f from A cross B to B cross A is 1, 2. And therefore f from A cross B to B cross A is bijective as it is 1 1 and 1 2. It is 1 1 and 1 2. Clear? Next example that we want to see here. Now example number 9. Let f from n to n be defined as f of n is equal to n plus 1 by 2 if n is odd, is equal to n by 2 if n is even, for or n belongs to n. State whether the function f is bisective justify your answer. Now see here two possibilities that n is odd. First of all, see, if you take 1, then what we get? 1 plus 1 by 2, that is 1. N is even, take 2, that is also 1. So on first look it is clear that it is not 1 1. For 1 comma 2 belongs to n, f of 1 is equal to 1 plus 1 by 2 is equal to 2 by 2, because 1 is odd, is equal to 2 by 2 is equal to 1. And what is f of 2? F of 2 is 2 by 2, because 2 is even. So that is also 1. And therefore, for 1 not equal to 2, we have f of 1 is equal to f of 2. And therefore, f from n to n is not 1 1. Now check it is 1 2 or not. Range of f is equal to f of n, n belongs to n, means nothing but n plus 1 by 2, n belongs to n union, because it is odd than that thing, even than this thing. So if we take 1, then we get 1. If we take 2, then also we get 1. If we take 3, then we get 2. If we take 4, then also we get 2. If we get 3, then if we take 4, n is equal to 4, then 2, n is equal to 5, then 3, n is equal to 6, then also 3, and so on. We get that is equal to n. So range of f is equal to n, and therefore f from n to n is odd. Sorry, is 1 2. Is 1 2. Therefore, it is not bisective. Why? As it is not 1 1. As it is not 1 1. Clear? Now next example. F from, let A is equal to R minus 3 and B is equal to R minus 1. Consider function f from A to B defined by x minus 2 over x minus 3 is f 1 1 and 1 2. Justify your answer. That we want to see. Now see, here A is equal to R minus 3 and B is equal to R minus 1. And f from A to B, f of x is equal to x minus 2 over x minus 3. It is easy to understand that why here they are removing 3, because that is denominator quantity here. So now we can see that for various value of x we get various value of f of x. So it will be a 1 1. And to show that it is 1 1, we start with two elements. For x1, x2 belongs to A, f of x1 is equal to f of x2. This implies, here it is understood that x1 is not equal to 3 and x2 is also not equal to 3 because they are in A, r minus 3. Clear? This implies x1 minus 2 upon x1 minus 3 is equal to x2 minus 2 upon x2 minus 3. So cross multiplication x1 minus 2, x2 minus 3 is equal to x1 minus 3, x2 minus 2. So here we get x1, x2 minus 3x1 minus 2x2 plus 6. On right hand side x1, x2 minus 2x1 minus 3x2 plus 6. Now see, it is easier to see that x1, x2 get cancelled, 6, 6 get cancelled. Take minus 2x1 on left hand side and take minus 2x2 on right hand side. So this implies minus 3x1 plus 2x1 minus 3x2 plus 2x2. This implies minus x1 is equal to minus x2 and this implies x1 is equal to x2. So what we proved, and therefore for x1, x2 belongs to A, f of x1 is equal to f of x2 implies x1 is equal to x2. Implies x1 is equal to x2. And therefore f from A to B is 1 1. Now for y belongs to B, B is equal to r minus 1. We want x belongs to A, r minus 3 such that f of x is equal to y. If we show that thing, then it is 1 2. Now for every y belongs to B, take x is equal to, now solve this one. X minus 2 upon x minus 3 is equal to y, implies x minus 2 is equal to xy minus 3y. So take this on left hand side, same time take x common, 1 minus y is equal to 2 minus 3y, implies x is equal to 2 minus 3y over 1 minus y. And that should be in r minus 3. So take x is equal to 2 minus 3y over 1 minus y. Now prove that it is not equal to 3. If 2 minus 3y over 1 minus y is equal to 3. Why we have to check this condition? Because it should be in A. That means it should be other than 3. Then what we get? 2 minus 3y is equal to 3 minus 3y implies 2 is equal to 3 and is not possible. And therefore x is equal to 2 minus 3y over 1 minus y is not equal to 3, and therefore x is equal to 2 minus 3y over 1 minus y belongs to R minus 3, and that is our A. So what we proved, and therefore every y belongs to B is equal to R minus 1, we have x is equal to 2 minus 3y over 1 minus y belongs to B, A is equal to R minus 3, such that f of x is equal to f of 2 minus 3y over 1 minus y. That is 2 minus 3y over 1 minus y minus 2 over 2 minus 3y over 1 minus y 3. 2 minus 3y minus 2 plus 2y. 2 minus 3y is equal minus 3 plus 3y. So here we get 2 cancel, here we get minus y, and here 3y cancel, here we get minus 1, that is y. So for every y belongs to B, we have x is equal to 2 minus 3y over 1 minus y belongs to A, such that f of x is equal to y, and therefore f from A to B is on 2, and therefore f from A to B is bisective also. Why? As it is 1 1s on 2. Now dear friend, this completes 1 1ness and 1 2ness and bisectiveness of a function. Now you are able to solve illustration number 1 to 14. 1 to 14. Clear? Next our aim is to start a new topic. How to compose two functions. Composition of two functions. A very important topic of this chapter. Composition of two functions. Now let us consider roughly idea to define composite function. Let us consider 1, 2, 3, A, B, C, 4, 5, 6. 1 to B, 2 to A, 3 to A to 4, B to 5. Clear? Now see, A, B, C. Now domain of, if I call this function f, if I call this function g, domain of f is this one. B is codomain, but what is range? Only AB. And what is codomain of G? That is C. Clear? That is codomain. Codomain of G. Now see, composition means image of image. See, image of image. But see, image of function f should be is a subset of domain of second function. See, here range of f is subset of B. Yes. So GOF, this composition exists and is a function from A to C, directly A to C. This is the composition. When range of this function, second function, should be subset of domain of first function, then that composition exists. And how to find an image? G of 1 is equal to G of f of 1, image of image. What is f of 1? F of 1 is B. And what is G of B? That is phi. Same way we can compute GOF at 2 also. So G of f of 2. G of what is f of 2? A. And what is G of A? 4. Same way we can find G of at 3 also. G of f of 3. What is f of 3? That is once again A. F of 3 is once again A. And what is G of A? 4. So this is the composition of functions. Clear? Now we have to define that things. If for functions f from A to B and g from C to D, if range of f is subset of domain of G, range of f is subset of domain of G, then G of f is defined and G of f is function from where to where? Domain of f, A to codomain of G, D. Also if range of G is subset of domain of f, then f of G is defined and f of G is function from domain of G, that is C, to codomain of f. Clear? And GOF at x is equal to G of f of x, and that should be for all x belongs to A. And here f of G at x is equal to f of G of x. That should be for all x belongs to C, because domain is C. But see, this is the definition of a composition of two functions. But how do we memorize or how we use this one? See, remember this box only. Then it is easy to find composition. See, if we wish to check the existence of f of G, what we need to check? If range of second function is subset of domain of first function, then f of G is defined. Then f of G is defined and f of G is from where to where? Domain of G to codomain of f. Clear? Keep only this thing in mind. Second thing, 1 minute, and f of G at x is equal to f of G of x for all x belongs to domain of G. Second thing, if range of f is subset of domain of G, then GOF is defined and is from where to where, and GOF is from where to where? Domain of f to codomain of G, and GOF at x is equal to G of f of x for all x belongs to domain of f. Clear? 1 minute. See, dear friends, to check the composition f of G, first of all, for two functions, find domain of both function, range of both function. And if we wish to see the existence of f of G, check that range of second function is subset of domain of first function. Range of second function is subset of domain of first function. Then f of G is defined. And f of G is from where to where? Domain of second function to codomain of first function, and is can be obtained with this formula. F of G at x is equal to f of G of x for all x belongs to T of G. Same way, if we wish to check the existence of GOF, check that range of second function should be domain of first function. See here, range of first function should be subset of domain of second function. Then GOF is defined, and GOF is from where to where? Domain of second function to codomain of first function, and GOF at x is equal to G of f of x. Clear? So this is the for composition. And now for f is defined from any set, then and only then composition exists, then f of G exists. Then f of f exists. That means composition of same function is exists only when domain and codomain are same for a given function. Clear? Next definition. Identity function. Identity function. For a not equal to phi, a function Ia from a to a, Ia at x is equal to x. That means image and pre-image are same for all elements of domain. Then Ia is called identity function. On set A. For example, if I write IR means what? Is a function from R to R, and IR at x is equal to x for all x belongs to R. That we have to understood. Clear? This is the definition of identity function. Or if I write IR plus means what? Is a function from R plus to R plus, and IR plus at x is equal to x, and it is true for all x belongs to R plus. Clear? Yes. Now from these two definitions, one more definition. Invertible function. Clear? Or inverse function. Just inverse function. Here, new definition. If for function f from a to b, if for function a to b, there exists a function g from b to a such that f of g is also identity function and g of f is also identity function. but it is identity function defined in domain of G, and this should be identity function defined on domain of F. Then G from B to A is called inverse function of F from A to B. This is the definition. Now see, then one condition, existence of inverse function, if F from A to B is 1, 1 and on 2, then inverse of F exists and it is from where to where, and F inverse from B to A. Keep one thing in mind, f of x is equal to y if and only if x is equal to f inverse y. Clear? See, this is the definition of composite function, identity function, inverse function, and existence of inverse function. First of all, we need to check the examples based on composition. Now see, one easy example is here, so that, of course, that is illustration number 18 and 19, so that if F from A to B and J from B to C are 1, 1 and 1, 2, 1, 1 and 1, 2, or bisective, then grow where to where? Domain of AF, that is A, to codomain of G. C is also 1, 1 and 1, 2, or is also bisective. Now see, here F is from A to B and G is from B to C. Here, now range of function f is always subset of its codomain, but that is what? That is domain of second function. So range of f is subset of domain of G, and therefore GOF exists, and GOF is from where to where? Domain of function f, that is A, to codomain of function G. Now, to show that for 1, 1 and 1, 2, for x1, x2 belongs to A, start GOF of x1 is equal to GOF at x2. This implies 0 of f of x1 is equal to 0 of f of x2. We can apply. Now see, G from B to C is 1, 1. Both are 1, 1. F is 1, 1 as well as G is 1, 1. So G of x1 is equal to G of x2 implies x1 is equal to x2 only when x1 and x2 are from domain. So here we need to check that. First of all, put the condition. x1, x2 belongs to A, and f is function from A to B. This implies f of x1 and f of x2 belongs to B, and use that G from B to C is 1 1. Clear? This implies f of x1 is equal to f of x2. Clear? This implies x1 is equal to x2, because x1, x2 is in A, and f from A to B is 1 1. So what we see? For x1, x2 belongs to A, graph at x1 is equal to graph at x2 implies x1 is equal to x2, and therefore G of from A to C is 1 1. Clear? Next, our aim to see one-to-ness. Here G from B to C is 1 2. So for every y belongs to C, we have B belongs to B such that G of B is equal to y. Now B is in B, and f from A to B is 1 2. So we have x is in A such that fx is equal to B. So replace this value, and therefore G of B is equal to y implies G of f of x is equal to y implies graph at x is equal to y. So what we proved? Therefore for every y belongs to C, we have x belongs to A such that graph at x is equal to y, and therefore graph from A to C is 1 2, and therefore graph from A to C is bisecting, as it is 1 1 and 1 2, as it is 1 1 and 1 2. Clear? Yes. Now see exercise 1.3. First example, first one. F is from 1 3 4 to 1 to 5, and G from 1 to 5 to 1 3. Let be given by f is equal to 1 2 3 5 4 1, and G is equal to 1 3 2 3 5 1. Write down G of F. But see, here I would like to solve in general this question. See, here domain of F is first element of every order pair of F is domain. 1, 3, 5. What is range of F? Set of second element of every pair of F. 2, 5, 1. Or 1, 2, 5. One and same thing. What is domain of G? First element of every order pair of G. 1, 2, 5. And what is the range of G? Range of G, set of element in second order pair, second element of every order pair, set of second element of every order pair. That is range of G. Which one is subset of other one? Also, first of all, mention that f of 1 is equal to 2. F of 3 is equal to 5, order pair 3, 5 means what? F of 3 is equal to 5. F of 4 is equal to 1. And G of 1 is equal to 3. G of 2 is equal to 3. And G of 5 is equal to 1. Clear? Now, range of F is subset of domain of G, and therefore GOF exists. And GOF is where to where? Domain of F, that is 1, 2, 1, 3, 5. 1, 3, 4, sorry, so 1, 3, 4. 1, 3, 4. 1, 3, 4. That is the domain of F. 1, 3, 4. Range of F, that is 1 to 5 subset of domain of G. So it exists from where to where? Domain of F to codomain of G. What is codomain of G? That is 1, 3. Clear? Repeat to see. This is the domain and this is the codomain. And GOF at 1 is equal to G of F of 1. What is F of 1? 2. And what is G of 2? 3. GOF at 3. G of F of 3. What is F of 3? 5. F of 3, 5. And what is G of 5? 1. 1, 3, 4. G of F of 4. F of 4 is 1. G of 1. And what is G of 1? 3. So what is GOF? 1, 3. 3, 1. And 4, 3. That is GOF. Similarly, here, see, range of G, range of G, here 1, 3, is subset of domain of F. Therefore, fog is exists. And where to where? Domain of G, 1, 2, 5. Codomain of, from domain of G to codomain of F. What is codomain of F? 1 to 5. So similarly, in this way, I am leaving this part for you. On same line, you can solve illustration number 15 and 16. Clear? Not 15 and 16. Yes, illustration 15 and 16. 18, 90 already seen. Clear? So, this one is for homework. Let us see one more thing. See, example number 2. Let F, G and H be functions from R to R. So that F plus C or H is equal to F of H plus C of H, and F into G or H is equal to F of H into G of H. We know that how to take sum of two functions, product of two functions. If F to R, G from B to R, then F plus G, F minus G, or F into G is function from where to where? A intersection B to R. That is the domain of F plus C, F minus G, or F into G is intersection of domain of F as well as domain of G. But that thing, this case is not arises here because all are function from R to R, so each one exists. Here F from R to R, G from R to R, and H from R to R. And therefore F plus G, F into G, F plus G into H, F O H, G O H, F into G O H are all exists, and they are from R to R. One thing, to show that two sets are equal, we need to show that both are subset of each other. To show that two functions are same, both functions should be defined on same domain, and both functions have a same images for all elements of codomain. Domain. Then we can say that both functions are equal. Okay. Now see, here F plus G or H is function from R to R, and F of H plus G of H is also function from R to R. Both defines on same domain. Now we need to prove that they have the same images for all elements into domain. Now for every x belongs to R, F plus G of H at x is equal to F plus G of Hx, that is F of Hx plus G of Hx, that is F of H at x, G of H at x, A4H, GOH at X. So what we proved, and therefore for every X belongs to R, A plus GOH at X is same as A4H, GOH at X for every X belongs to R. That already written. And therefore both functions are same. A plus GOH is equal to A4H plus GOH. Similarly, F into G OH is function from R to R. FOH into GOH is also function from R to R. Both are defined on the same domain. Now we need to prove that both have the same images. For all X belongs to R, F into GOH at X is equal to F into G of Hx is equal to F of Hx into G of Hx. This can be written as F(H) at X dot GOH at X. This can be written as F(H) into GOH at X. So both have the same images. And therefore, for all X belongs to R, F into G composition with H have a images for X belongs to R, same as FOH GOH at X. And this one is true for all X belongs to R. And both functions have the same images as well as both are defined on the same domain. And therefore they are equal. Is equal to FOH into GOH. Now dear friends, now you are able to solve illustration number 1, 2, 21, 22. See, illustration number 1, 2, 22. Friends, see, up to lecture number 6, illustration number 1 to 22 for homework, same way you can see some example based on this one. Miscellaneous exercise example number 1 I am leaving for you, and example number 3 also. Here we need to find composition of composition. Clear? So I am leaving this part for you. Up to this day, I hope you will be agree with me. Rest of thing we are going to see next lecture.